Hi everyone. Today I'm going to walk you through solving an interesting question, dot product of two sparse vectors. So the question says that given two sparse vectors, compute their dot product. And it has some explanation regarding to implement a class sparse vector. And with a sparse vector, we initialize the object with the vector norms, and with dot product compute the dot product between the instance of sparse vectors and vec. So what is a sparse vector? A sparse vector is a vector that has mostly zero value, and you should store the sparse vector efficiently and compute the dot product between two sparse vector. This question has a follow-up, and its follow-up is what if only one of the vectors is a sparse? So we have some example here. For the first example, we can see that the dot product for nums1 and nums2 is simply the summation of the values at the same index, and we can see that the result is 8. So this question has different solution, and I want to go through each one in the next section. Okay, so as I said before, we should provide the brute force approach for every question that they are asking during the interview. Here, the brute force approach is to going through each index of nums1 and nums2 and calculate the product of their value. So we have 5 elements here. So this is index 0, index 1, index 2, index 3, and index 4. Okay, so we are going through these 4 index and calculate their nums. So let me to say that the first solution is brute force approach, and we can say that okay, going through all of this value is 1 times by 0 plus 0 times 3 plus 0 times 0 plus 2 times 4 plus 3 times 0, and this is equal to 8. Okay, so what is the time and the space complexity here? For this solution, the time and the space complexity is same as this. We don't have anything to save here, so the space complexity is O of 1, and for the time complexity we only go through the length of each array, so it's O of n plus n, since the question says that the length of these two is same as each other, so this is O of n. So actually it's not a bad time complexity or a space complexity, but what is the problem with this solution? The problem with this solution is that we have to do a lot of useless operation. For example, this is a useless operation, this also, and this one also. So we have to do a lot of operation here to do a lot of operation. Okay, so what we can do to remove or ignore this operation? Here is the second solution that we can do. Okay, so let me to clean this part. Okay, so the second solution is we can use a hash map. In the hash map, we can only save the values and the index that the values are not 0, so saving the non-zero value. Okay, so for example, for this one we can use a hash map. H1 is, we can use the index as key and the value as value. H1 0 is 1 and we have 3 that is 2, and we have 4 that is 3, and we have h2 that in h2 at index 1 we have 3, at index 3 we have 4, and we don't have anything left. Okay, so now we are moving to one of our hash map and says that, okay, if we have that index in the next hash map, calculate the product of these two index and add them to the result. So for example, here we at the first step we go to index 0. Do we have that in the second hash map? No, we don't do anything. We go to the next one. Do we have 3 in the next hash map? Yes, so we have 2 times 4. And then we go to the next one. Do we have index 4 in the next hash map? No, so we only have this index, and the result is 8. So here, what is the time and space complexity? For the time, we have to go to each array to build the hash map. So we have O of n plus n, which is O of n. And then during the calculation, we also going through the hash map, but it has the same time complexity as before. For the space complexity, in the worst case, we have to save all of the values in the array. So consider an array as 1, 2, 3, 4. All of these values are non-zero, so we have to save all of them in the hash map. So the space complexity is O of n. But overall, we can say that is O of L, which L is the number of non-zero elements in our arrays. So this is the second solution, but this is not the best solution that we have, since in some cases that our array is too long, maybe collision happen in our hash map, and then we cannot reach to this value in O of 1, since we know that searching from a hash map is O of 1, and it's a valid point, but in some cases maybe we have a collision and this increases. So overall, since hash map come with potential issue like hash collisions, it's better to save this index and value in a list and then calculate the dot product of the two array. So let's go with the third solution here. Third solution is to save the index and value in a tuple in a list. Okay, so to solve the collision problem and optimize the solution, we can use a list of tuples, and each tuple contains the index and the value of only the non-zero elements. Okay, so I mean, we can go with the first one as L1, that is from this the first array. We can say the first one is index, the second one is value, and then we have 3, 2, and then we have 4, 3. And for L2 we can say that 1, 3, and 3, 4, and that's it. And then same as hash map, we are going to L1 and say read the index is 0. Do we have that in L2? No, so we don't do anything. Here read the index, and value is 3 and 2. So do we have index 3 in L2? Yes, we have that. And what is the value? Is 4. So it's 2 times 4, that is 8. And what is the time and the space complexity for this one? Same as Hashmap, the time complexity is O of n, since we have to go through each array at least one time. And for the space complexity, we have O of n, since we have to build this array into a list, and in the worst case that the number of the non-element 0 are same as the length of the array, this will be O of n. So yes, this is the best solution for this question. Okay, so before I go to the coding section, it's better to explain how we should write the code for this part. Okay, so as I said before, we can save this non-zero element into a list, and L1, L2. L1 is 0 and 1, and then 3 and 2, and 4 and 3. For L2 we have 1 and 3, and 3 and 4. Okay, so we know that the first one is the index and the second one is the value, and we want to go through these two lists. So we need two pointer 1, pointer 2. We can use a while loop and say that while p1 is less than the length of this array and p2 is less than the length of this list. Okay, so with this way, at the first step we set p1 and p2 to p1, p2. At the first step is 0. With this we read the index 1 and value 1, and index 2 and value 2, and then we can check these two indexes to each other. If they are equal to each other, we can product value 1 and value 2 and add them to the result. But if not, we should increase one of the pointer here. So for the first example, we can see that index 1 is 0, index 2 is 1. So these two are not equal to each other. We can not add anything to the result. And we have to increase this pointer to check that maybe we have another value at index 1 that is same as this one. Consider a scenario that we have a number like 2 here. Then we have 1 and 2. So we have to increase this index to check that, okay, do we have any value at index 1? And we can see in this scenario we have a value here. So in this scenario, if index 2 greater than index 1, we have to increase the pointer 1 by 1. And exactly same as this, if index 1 greater than index 2, we have to increase the pointer 2. And if the index are same, we can definitely go with product of the value at those two index. So here at the first step, index 1 is less than index 2, this one is less than this, we increase the pointer 1. So let me to write with this. At the first step, p2 is here, p1 is here, index 1 is 0, index 2 is 1, this is less than this, we increase the pointer 1 to here. So now index 1 is 3, index 2 is still 1. So we can see that since index 1 is greater than index 2, we increase this pointer. Now p2 is here, and right now index 1 is 3, index 2 is 3. We can calculate that the result is result plus 2 times 4, that is 8. And here we don't have anything left, we cut the while loop. Okay, so I hope it's clear now, and now we can go to the coding section. Okay, so here I want to implement the tree approach that we already discussed, and you don't need to implement the naive approach and Hashmap approach in your interview. So since we have a class here, we can say that we can provide this line, and then at the first step our result is 0, and we can go through each index of our array and add that value to our result. So the only point here is that the second vector is vec.nums, and its value at index I is vec.nums I. So, and then by end of this we return the result. Okay, and yeah, it works. If we submit that, let's to see. Okay, I don't know that how much this result is accurate, but it only beats 80% of submission. So let's go with the Hashmap approach here. The Hashmap, we can say we can go through the index and value in our nums. If value is not equal to 0, we can say that self mapping of index equal to value. And for the result, we can set at 0 at the first step, and then going to the index and value in our hash map. And if that index is in the second hash map, then we can add that. We can add the value 1 times the value at index in Hashmap 2, and by end of that we can return result here. So do we have any error? Let's check. Okay, so it seems better here. Let's go with this, the last solution. We can define a list as data or non-zero, which is a list, and for index and value in nums. If okay, so what's going on here? I think that okay, so if value is not 0, we should add the index and value. Okay, so we have the index and value of each vector here, and then same as before, we can add these two non-zero lists. And as I said before, we should go through the arrays, and if we have that arrays in in the second list, we can do some calculation about how can we move through our array or the list here. So we can use a pointer 1 and pointer 2 as 0. Pointer 1 is the pointer that we want move to the first list, and pointer 2 is for list 2. And we can say that while we can use a while loop and say that while p1 is less than the length of the non-zero, and p2 is less than the length of vec non-zero, we should do the following. So we read the index 1 and value 1, which is non-zero at pointer 1, and index 2 and value 2, which is vec non-zero p2. So if these two indexes are equal to each other, we can add their production to our result. So if index 1 equal to index 2, we can add value 1 times value 2. Here, don't forget to add 1 to our pointer. So we should add 1 to pointer 1 and add 1 to pointer 2. And if index 1 is less than index 2, we should add pointer 1 here, and if not, we should add 1 to pointer 2. Okay, so we can see that this can work. I will provide. Okay, for the follow-up question, if the follow-up question is, what if only one of the vectors is sparse? So in this scenario, we can iterate over the sparse vector and save the non-zero element and use the binary search to find the position that match with the indices in the dense vector. And this can help us to avoid iterating through all 0 elements in a sparse vector and optimizing the computation. So I think that they don't need to implement the binary search by yourself. You can use bisect left in Python to find the position and then compare the position with the index. Okay, so we can discuss this more in the comments. Thank you.